All right, so let's get started for today. If you remember, last time we made it through um, the carboxylic acid um, chapter, and I guess we had just started talking about the carboxylic acid derivatives and their nomenclature. So we made it all through the nomenclature. Now we want to get to the point where we're talking about reactions. And we want to talk about reactions of carboxylic acids in a little more detail because that's going to really lead into how we prepare uh, carboxylic acid derivatives from carboxylic acids. And so I'm going to say reactions of carboxylic acids, and initially, but we're going to move very quickly into all of the nucleophilic acyl substitutions. And it's going to be hard to, we're going to keep things in categories of functional groups because, as I said, as we go through these, all these reactions are going to be transformations from one carboxylic acid derivative into another, and then vice versa. So there's going to be a lot of redundancy as we go through this. So really just remember what we're talking about here is the general reaction, nucleophilic acyl substitution. But if you take carboxylic acids, you can convert them into acid chlorides. Because remember, to emphasize, acid chlorides are a carboxylic acid derivative. So how can we take a carboxylic acid and form an acid chloride? And you can do that with several different reagents. Some are more common than others. One of them we've seen before, thionyl chloride. Remember, that was a way of taking an alcohol and converting it into the alkyl chloride. So here we're kind of doing the same thing, but it's just an OH that's attached to a carbonyl reacting with thionyl chloride and substituting a chlorine for the OH, right? But you can also use PCl3, which is kind of a relative, right, of PBr3 that we've already seen converting an alcohol to an alkyl bromide. Okay, so again, it's going to be substituting a chlorine for the OH of the carboxylic acid. And then there's oxalyl chloride, which is this. And that's a new reagent, and it's kind of like the simplest acid chloride you can think of, but it's kind of a mild reaction, but it can form acid chlorides. But by far, this is the most common reagent that's used. Okay, so in general, what is the reaction? So if you're doing your flashcard, what is the reaction you're going to show that would convert a carboxylic acid into an acid chloride? And I'm just going to use this example, demonstrating that it doesn't matter if you have alpha beta unsaturation in your carboxylic acid. So you have the carboxylic acid, simple reaction, thionyl chloride. That's what you would put on your arrow solvent, something like chloroform. The product of this is going to be the acid chloride. Okay, and so again, what we're going to see in these reactions, and by the way, let me just show you, since this is the first time you're introduced to this, your byproducts, which you wouldn't have to show in a reaction section, but your byproducts are HCl and SO2. But basically, with a nucleophilic acyl substitution reaction, remember, all of these reactions are simple. What's in the box gets substituted with the nucleophile. And that's all the product is. You're substituting one group attached to the carbonyl with another group. It's that simple. Okay? Now, if you were to use PCl3, the reaction is exactly the same. Both of those work. Thionyl chloride, SOCl2 is by far the most common. All right. Mechanistically, we don't have to look at it because mechanistically they behave exactly like the reaction we talked about with alcohols being converted to alkyl halide. So if you're not sure of the mechanism, just go back and look at that. Operates exactly the same way. What about conversion into acid anhydrides? So how do we take a carboxylic acid and convert it into an acid anhydride? You do that simply by taking a diacid. Let me redraw this one the same way. You take this diacid and all you have to do is heat it. And this reaction occurs where it expels water. And so you basically form the acid anhydride plus water. All right? And it works best in a case like this where you're forming a ring. It works best for 5 or 6 membered rings in the context of what you're forming. Okay? And that's basically, that makes sense to us because remember way back in the October, God, that seems like forever ago, where we were talking about the strain in rings, and we were going through 3-membered ring, 4-membered ring, 5 and 6-membered rings. Remember we saw were the most stable. So when you're forming a ring like this in a reaction, 5 and 6-membered rings are going to be by far the easiest and most favorable. Okay. Now, you don't have to form cyclic anhydrides. You could also do something like as simple as acetic acid, right? And heating it. And it will form the anhydride. And if you're thinking about the stoichiometry here, you're really basically, if you have 100 molecules of this, you're only forming 50 of that because, the understood thing is you have 1 molecule of this reacting with another molecule of this, forming 1 molecule of that. But the 2 is understood. You don't have to write it. You just know that 2 of these molecules are coming together to form that 1 molecule. Okay? So that's how you can form anhydrides. What about conversion of a carboxylic acid into esters? Again, these are all carboxylic acid derivatives. How can we form these functionalities from a carboxylic acid? And the simplest way to do this is just in an SN2 reaction. And that's going to be where you take the carboxyl form of your carboxylic acid, and let's put the counter ion on there to make it sodium. And you form this carboxylate as we've seen just by treating it with a base. Okay? And then once you form this, you can treat it with an alkyl halide, in this case methyl iodide, and you're going to form the ester. Like that. All right? And then what else are you going to form? Just to keep up with things, the counter ion is then going to be with the iodide. Okay, simple SN2 reaction. These work, but there's a limitation. What do you think the limitation is? I mean, at this point, we're only a few lectures away from you being done with organic chemistry, so you're really experienced by now. So if this is an SN2 reaction that you're doing between this nucleophile and this electrophile, SN2, what do you think the limitation is? The alkyl halide has to be primary. Okay? That's the standard limitation we have with these types of reactions. Okay, so that's one way to make an ester. So because it has a limitation, we would hope that there are other ways of doing it, and there is. There's something called the Fischer esterification. Reaction. And again, this This goes way back, probably into the 1800s, so they really did name reactions after people back then. And this is just a way of making an ester by taking the carboxylic acid, and let's use a Fischer example. You use one from the literature. Let's put a CH2 there, and then my carboxylic acid. So we take an acid and then we just treat it with an alcohol. And let's use ethanol here. Okay? And the reaction is acid catalyzed, so you have to have a little HCl in there. Okay? And then basically the products that's going to form, and again, we're kind of getting experience with this now, right? This is what's in the box. So I'm going to substitute what's in the box with the nucleophile. And so my product is going to be this. This stuff is just too simple. Correct? That's going to be the product. Plus water, which is from, this is the leaving group, right? So it's leaving as water. So again, simple, straightforward nucleophilic acyl substitution type reaction. So we should be able to think about what the mechanism of this is. It's worth looking at the Fischer esterification mechanism because it's an interesting one. Okay, because it demonstrates how simple this is. Okay, because remember, if all of these are nucleophilic acyl substitutions, the mechanisms are all going to be very, very, very similar. Okay, so we have our carboxylic acid. It's acid catalyzed. By now we know what that means. If it's acid catalyzed, that means we're going to be making the carbonyl more electrophilic. That's what always happens with acid catalysis. So that means if I have HCl present here, what am I doing? I'm basically protonating the carbonyl. And so that means I'm going to produce this short-lived intermediate because then my nucleophile, and let's just use a generic alcohol. My nucleophile is the alcohol, right? The alcohol was not made more nucleophilic because that would have happened if it were base catalysis. Here it's acid catalysis, so it's my neutral nucleophile. And as I'm doing this, what does it kind of look like thus far? Remember, always think about the big picture, the similarities. This is looking a lot like acetal formation, right? Neutral alcohol reacts with the electrophilic carbon of the carbonyl, breaks the pi bond, moves the electrons up to the oxygen, right? Forming a tetrahedral intermediate, which would look like this. The carbonyl oxygen was already protonated, so that's it here, right? And then this is attached to the R group and the OH. So those are the substituents that were present on the carboxylic acid. And then what I've done is I've reacted now with that neutral nucleophile. So it's going to have a plus charge like that. Okay? Now what happens? Well, we've seen this situation before, right? We have a protonated oxygen and we have an OH group. This is just simply a proton transfer. Right? And when that happens, what happens when you have a proton transfer? This OH is now protonated and this one is now neutral. Okay, so what I have now is that protonated OH, which makes it a good leaving group. And remember, in a nucleophilic acyl substitution, this is going to be the leaving group. And so what I've done is I've produced that OH as a better leaving group. So now when I have, and by the way, this H comes from that structure above. I want to make sure that it's not confusing anybody. I'll move it out of the way. So then here I have water present. That water pulls a proton off of this OH. That moves those electrons in to reform the carbonyl. And when it does that, it spits off the leaving group. Okay, and so the result of that electron pushing, I'm going to show on the next board. Now you've got the magic of digital technology because you could have frozen at that point to make sure you got the mechanism all down. But at that particular point, what I have formed is now I have this ester, okay, and I've also produced what? H3O plus. So therefore this reaction is acid catalyzed. Now it has been shown that this carbon that I'm putting a dot in absolutely did come from the alcohol. That's how this mechanism was initially, way back when, supported. If you labeled this oxygen, you'd be able to follow it from alcohol to being present in the ester. And that's how that whole nucleophilic acyl substitution mechanism was kind of developed, because we know that this, what's in the box here, is what substituted for what was in the box, which was the OH. So this oxygen is lost. Okay. All right. Fischer esterification with mechanism. Okay. There's another way of making an ester, but it's limited to only making methyl esters, and it's using diazomethane is a reagent that is then reacted with the carboxylic acid. And so in general, if you were doing your flashcard and you have a carboxylic acid, you're going to react it with diazomethane, which has this formula, CH2N2. This is diazomethane. It's a reagent, and the result is the formation of the methyl ester. Now it can only be used for methyl esters, because diazomethane, it only has this CH2. That is what then is incorporated into the acid to make the ester. Now it's important, this is not a nucleophilic acyl substitution reaction. This is mechanistically completely different. It probably involves radicals. It's not a mechanism we want to look at. I will talk a little bit about diazomethane, because I've done this reaction numerous times. Diazomethane is explosive. I mean, like bomb grade explosive. It's bad. And it's shock sensitive. It's kind of like when we were talking about the ethers going bad, getting the peroxides in them. Well, this is even worse. So diazomethane is something that you have to produce in situ. So you have to take your reaction vessel and you have to generate the diazomethane. And then you can add your acid to it to then end up forming the ester. But here's the thing. Even two pieces of glass or two glass surfaces touching each other is enough to make that explode. So you can't transfer your solution of diazomethane, you can't produce it anyway where you'll put anything down in there where two surfaces of glass will touch, or the whole reaction explodes. So you have to use plastic. And you also, these round bottoms that you use in the lab are sometimes have ground glass. And so, there's so many potential dangers. So usually you buy this kit that's a diazomethane formation kit that has all plastic pipettes. It's coated glass surface, so you eliminate all of that. So, simple thing is this reaction works really well if you're willing to risk losing appendages to make your ester. Oh, and by the way, that there is a byproduct of nitrogen gas that's produced in that. So really all you need to know for this reaction is this, that you can use diazomethane to convert the carboxylic acid into the methyl ester. All right. So that's how we can take carboxylic acids and convert them to esters. Okay? Now, the next functionality we want to talk about is acid chloride. So now we have gone from carboxylic acids and their reactions, and now we're really into the carboxylic acid derivatives, because now we're going to talk about acid chlorides. And so we're going to do the thing where we talk about how to prepare them, and then we're going to talk about the reactions they undergo. Okay, but you can see where the redundancy is going to come in here, because I'm about ready to ask, well, how can we produce acid chlorides? Well, we just talked about that, right? You can produce them by taking a carboxylic acid and reacting it with thionyl chloride, and we said that gave you the acid chloride. So this is what I mean about redundancy. It's a reaction of a carboxylic acid, but it's also the preparation of an acid chloride. Okay, and we saw that there were several reagents that did that. Okay, so once we formed our acid chloride, what reactions will acid chlorides undergo? All of these reactions are going to be nucleophilic acyl substitution reactions, right? And so they're going to be really easy to predict. And I'm going to use, my notes have an A, B, C. I'm going to use one. First reaction, okay, hydrolysis. So that means basically I'm going to take, by that name, hydrolysis, that means I'm going to take an acid chloride and I'm going to react it with the nucleophile, and the nucleophile is going to be water, right? What is the product of this going to be? Here's what's in the box. Here is my nucleophile. So that means the product is simply going to be the substitution where the nucleophile has substituted for what is in the box. That's how simple it is. So just the fact that I know I'm reacting this with water, I know that the nucleophile is OH. And so I'm going to produce the carboxylic acid. Okay? Really, really simple. Do you want to look at the mechanism of that? Let's do the mechanism of this one, just to be able to show it. And then you'll see that for the rest of these, it'll be the same. So here is my acid chloride, and I'm going to react it with water. Okay? And basically, water is going to come in as a neutral nucleophile, attack the electrophilic carbon and the carbonyl, push these electrons out to the oxygen, forming the tetrahedral intermediate. We're going to see this a zillion times. Already seen it a zillion times. Okay, so here is a bond to the R that's attached to the carbonyl, and that means I'm also going to have my Cl here, and then I've added my neutral water like this, and you're thinking, you know, that looks similar, right, to every mechanism we've looked at for the past couple weeks. Okay, and since it's a substitution, this is going to come back in and reform the carbonyl, and the reason is I have two leaving groups here. So I could come back in and displace water, but then I'd just be doing the reverse reaction, right? So the reaction is reversible, right? But if it comes back in and reforms the carbonyl and kicks out chlorine, then I have formed what? I have formed that intermediate, and then I have Cl minus that came off as a leaving group. It pulls a proton off, moves the electrons into O. How many times have we seen that happen? Some Lewis base that pulls a proton off our neutral water that is reacted as a nucleophile. I mean, it's getting to the point where there's so much redundancy. Everything is so simple. There is your carboxylic acid and the HCl byproduct. Okay? Nucleophilic acyl substitution reaction. Okay, so going along in that same vein, reactions of acid chlorides. What do you think is going to happen if I take an acid chloride and react it with an alcohol? It's called alcoholysis. And so my nucleophile here is going to be just an alcohol. And so what do you think is going to happen before we look at anything else? And let's use a generic alcohol. What's going to happen if I react this alcohol with the acid chloride? What's in the box gets substituted with the nucleophile. So therefore, an acid chloride reacting with an alcohol under nucleophilic acyl substitution, what is in the box is the leaving group. This is the nucleophile. So all I have to do is stick the nucleophile there, and oh look, it forms esters. There's no way you could miss the transformation for any of these on the next test, because all I'm doing is sticking this where that is. Okay, it's that simple. Okay, now usually when you do this, you have pyridine present. Okay, and that's simply because you're producing HCl. And remember, pyridine is one of those things that captures the HCl. Okay. Another example of this that's specific. Say you have that acid chloride, and let's react it with propanol. Propanol. Presence of pyridine. All I'm going to do is substitute this for what's in the box, and I end up with that ester. All right? So again, following along with this vein, so I took water and reacted it with an acid chloride, and I got a carboxylic acid. I took an alcohol and reacted it with an acid chloride, and I got an ester. So what's going to happen if I react it with an amine? Aminolysis. And that's going to be reacting it with, an amine. And it can be, primary, secondary amine. And so basically that's going to mean, let's do a simple specific case. So I have my acid chloride, and I'm going to react it with methylamine. Okay. First, what's the product going to be? Well, what's in the box is going to be substituted with whatever the nucleophile is. And the nucleophile here is an amine. Okay. So chloride is the leaving group. This is the nucleophile. Therefore, I know the transformation is going to be simply the formation of the amide, because what's in the box got replaced with the nucleophile. Okay? Now mechanistically, this one's a little bit more interesting. Okay? Because it turns out that you need two equivalents of amine for this reaction to occur. And why do you think that might be? Well, it's a mechanistic situation, because as we've seen in the other cases, you're producing HCl in the reaction. Okay, so you have one molecule of acid chloride react with one molecule of methylamine, and you form one molecule of this, plus a molecule of HCl. Well, that molecule of HCl is going to interact with a molecule of the amine. This is kind of, remember back when we talked about amines reacting with ketones and aldehydes, and we talked about the whole pH profile, that you had to be careful if your amine nucleophile was in the presence of acid, because what happens is you'll protonate the amine with this acid that's formed. So this then gets taken out because it produces a salt, a hydrochloride salt. This falls out of solution. So what I've done is I've removed a molecule of my amine. So if I continue this process, for every amide molecule I form, I'm also getting rid of a molecule of the amine. And so I'm getting rid of two molecules of amine for every amide I form. And so basically to remedy that, all you do is use two equivalents of the amine. So one goes to forming the amide, one's converted to the salt, and no one's the wiser. Okay, because you then will be able to get theoretically 100% yield. Okay, and remember on a reaction section, you assume it's excess. So the only thing you'd have to worry about is if for some reason somebody put one equivalent here, then you know that the reaction is not going to go to completion. Okay, but if there's nothing indicated, you assume that there's excess enough for the reaction to complete, so you would assume there are two equivalents. All right. Next nucleophile, you can reduce acid chlorides, and we've already seen this. So you can reduce an acid chloride into an alcohol, and remember we did that. You already have your flashcard for this. Acid chloride reacting it with LAH, followed by an aqueous acid workup. Okay, and the result of that is going to be the formation of the alcohol. So this is review. Here, remember LAH, your nucleophile is H minus. Okay, and so basically, you're still replacing an H for this chlorine. So what's in the box was replaced with an H, but then remember a second equivalent of H minus added to the aldehyde that formed. So just a reminder, if you forget, one equivalent would give you the substitution, where the nucleophile replaces what's in the box. But then the second equivalent of hydride comes in, and that's where you actually form the alcohol. Okay, so that's review, just reminding you of that. Okay. Now, with this in mind, wouldn't it be nice if there were a way of partially reducing this? What if we wanted to convert an acid chloride into an aldehyde? Is there a way of doing that? That would be really nice, wouldn't it? So can we reduce that acid chloride into an aldehyde? And remember, that would fall under the category of partial reduction, because you would be stopping the reduction after one equivalent of hydride reacted. And you can do that. What you use is a less powerful reducing agent. And we've seen that already with Dibol when we were talking about reductions into aldehydes. But with with an acid chloride, you have to use this reagent. And it is a lithium hydride reagent, kind of like what we saw with Dibol. But the R group in this case is huge. Okay? And so that's basically, you have your lithium and aluminum, and here's the reactive hydride. And then you have this, basically, you have three tert-butoxy groups attached. So there's this huge steric mass, okay, that only allows one equivalent of hydride to react with the acid chloride. And therefore you will stop after that one reduction. So therefore, if you had, and this is for your flashcard, if you had an acid chloride like this, the reagent, and it would actually be shown like this on the test, written out completely like this to demonstrate the bulk of this, okay, followed by the acid workup. Okay, and just in case you're having trouble seeing, lithium, aluminum, H, and then in the brackets it's OC, parentheses, CH3, close parentheses 3. So there are three methyl groups attached to that carbon, right, which is then attached to the O. But then there are three of these that are attached to the aluminum. Okay? And so that then would yield, and I'm going to draw it up here because I ran out of room. 1, 2. That would simply stop after the substitution. So then what's in the box is substituted with the nucleophile, which is the H. Okay? So that's a way of partially reducing to get the aldehyde. Okay? Now another reaction we've already talked about of acid chlorides is their reaction with organometallics. Okay, and so the first of those organometallics that you remember talking about, if you have an acid chloride and you react it with a Grignard reagent, and let's just use generic, okay, followed by acid workup. And remember, just like we just talked about with the hydride, when we talked about Grignard reagents reacting with acid chloride, remember you would initially get the substitution, and then that would be followed by the addition, because 2 equivalents of your Grignard would react. You've already been tested on this reaction. I'm just showing it to you again, because basically what happens, and I'm going to put a prime on my R group in the Grignard. Remember what happens when you have an acid chloride and a Grignard, you add 2 equivalents of the Grignard, so you end up always with a tertiary alcohol. Okay. Grignards reacting with just about any carboxylic acid derivative are going to give a tertiary alcohol. Okay. Now, what if you wanted to stop after 1 equivalent? What if you wanted to find a way to do a partial alkylation? Like, let's just say that I wanted to form the ketone. Okay. Is there any way to do that? Yeah, partial alkylation. Remember, we just used what? The Gilman reagent. We've seen this before already too. Gilman reagent will only react once, and so it'll go from the acid chloride to the ketone. So just like I saw with the hydride, there's a way to do the 2 equivalents to go all the way to alcohols, but there's also a way of stopping. In the hydride, I could stop at the aldehyde. With the Gilman, I can stop at the ketone. So very effective reactions, because I can do full or partial reductions or alkylations. Leaves open a lot of, especially synthetically, a lot of options here. All right. Now we can also then move forward now from acid chlorides to acid anhydrides. Now, if you notice, what we're doing is we're trying to kind of stick to the same order of reactivity that we talked about, where we said acid chlorides were the most reactive of the carboxylic acid derivatives, right? And then followed by acid anhydrides. So now we're transitioning to acid anhydrides. But in that transition, we're also, as you're going to see, still kind of talking about acid chloride reactions, because you just can't separate these things. How are you going to prepare an acid anhydride? Well, one of the easiest ways is to take a carboxylic acid that's been converted to, the carboxyl, and you're going to react it, and I'll put the counter ion there. You're going to react it with the acid chloride. Let's make that a CH3. Okay, and so what's going to happen here? Well, the acid chloride is my carboxylic acid derivative. This is my nucleophile. Nucleophile reacts with the electrophilic carbon of the carbonyl, breaks the pi bond, moves the electrons out to the O. And then remember what's going to happen, that's going to close back in, and you're going to kick off the chlorine. So what's in the box gets replaced with the nucleophile. And so therefore, the product of this, there's my nucleophile, and it's replacing chlorine, and so I end up forming the anhydride. It's just nucleophilic acyl substitution. It's a reaction where you're taking an acid chloride and reacting it with a carboxyl group. So we could classify this as a reaction of acid chlorides. But it's also preparation of acid anhydrides. Okay, so you see the redundancy? All right, but to make these different functional groups, we're basically transforming one carboxylic acid derivative into another. That's how these reactions work. Now, what is interesting about this reaction? We've already talked about another way of preparing acid anhydrides. Remember, it was just taking two equivalents of the carboxylic acid and heating it, and you could form anhydride. So that was another way of preparing anhydrides. But by nature of that reaction, if you remember, it was always forming these symmetric cases. And I'm going to emphasize this because it's important. And so we talked about also being able to take something like acetic acid and heating it. And it would give us the same product we just saw being made by this other method. So both of these methods would make that same acid anhydride. But what is the difference? When you're using this method, it's two equivalents of the same acid coming together. So your anhydride's symmetric. You have the same R groups on either side. Okay? What happens if you wanted to make what's called a mixed anhydride? What if I wanted different R groups on the different sides? Could I do this? Let's just take acetic acid and this acid, heat them, and I should be able to make the mixed anhydride. Because these two R groups are now different. It's not symmetric. So how well do you think this reaction is going to work? That's when I wish you were here to answer me. This ain't going to work well. Why? Because I might have two of these reacting together. I might have two of these reacting together. And then I might have, these reacting with each other. So you're actually going to form three different anhydrides. Two of them would be symmetric and the other one would be mixed. So an awful way of doing it. Okay? But the method we just talked about, where you first form the carboxyl and then react it with the acid chloride, and I'm going to use this acid chloride now. Now, these two molecules are the only things that are going to react. Two of these are not going to react with each other. Two of these are not going to react with each other. It's always going to be nucleophile reacting with the electrophilic site of the carbonyl, breaking the pi bond, moving the electrons up to the oxygen, coming back in, reforming the carbonyl, breaking that bond to the chlorine. It's a leaving group, and then you're going to form what was in the box, gets substituted with the nucleophile, and I have produced this mixed anhydride. And that's the only product. So this method is how you make mixed anhydrides. All right? Isn't chemistry fun? Okay, so we're approaching a stopping point. I think that we basically have 2 more lectures after today until we're done with the semester, and we're making progress. We'll go as many lectures as we need to finish the material, because I think on my books I have 2 more after today, and we should be able to finish with that. Okay, but now what other this is a new way of making mixed anhydride. So we are reminding ourselves of a method of making the anhydride, and now I just showed you a new one. And so now we're at the point of reactions. We'll go ahead and start talking about this, and that is, what are the reactions that acid anhydrides will undergo? Okay, well, just like we saw with acid chlorides, these are going to be nucleophilic acyl substitution reactions, right? And so if you take an acid anhydride, and I'll just use a simple example, the acetic anhydride, and we react it with a nucleophile. Well, let's start with amines. So what will happen if I react an acid anhydride with the nucleophile being an amine? What is the product going to be? Let me draw just a primary amine here. What do you think the product is going to be? We can predict this, right? Here's what's in the box. Here's my acyl group. This is what's in the box. This is my nucleophile. So what's in the box is going to be substituted with the nucleophile, and therefore when I have an acid anhydride and I react it with an amine, I'm going to end up forming an amide, because this nucleophile is what's substituting for what was in the box. So transformations, simple, right? Simple. All you do is substitute what is the Y group, the leaving group, with what the nucleophile is. Okay? And so that is a way of converting them into amides. Okay? And that's really the primary reaction of acid anhydrides, is making amides. And just to give you an example of one, that might have a little bit of application or interest to you. If you do take acetic anhydride and react it with this amine, and it's a substituted aniline, but you still have the amine functionality. You have an OH here. You react these things together, and what you form, remember, here's what's in the box. You're substituting it with the nucleophile. So what you end up with is that amide, okay, which is acetaminophen. You ever heard of that? So this reaction does have some application medicinally. That's how you make acetaminophen. Okay? And conveniently enough, using the same anhydride chemistry, if you take this, and here your nucleophile is the OH, you can react it with an acid anhydride. Here's what's in the box. Here's my nucleophile. It's going to react with the electrophilic carbonyl. So this nucleophile is going to substitute for what's in the box. And that will give you this. Which is also an interesting compound that you might look up. All right? So these reactions are pretty easy to predict. And that brings us to the next functionality, esters. Okay? Preparation. Preparation of esters. Well, my goodness. We've already talked about preparation of esters. In fact, there's nothing but review here, because we know that we can take a carboxylic acid, because esters are carboxylic acid derivatives. We know, because we've talked about these in the reactions of carboxylic acids, right? We know that if we take this and react it with an alcohol, an HCl, that's Fischer esterification. We talked about it just earlier in this lecture. That's one way of preparing an ester. We've already talked about the fact that you can react it with a base, like sodium hydroxide, followed by an alkyl halide as long as it's primary. Remember, we talked about that earlier in this lecture. It would give you, it would convert the carboxylic acid into the ester. I'm going to put a prime on that. Remember, this is the one that was just an SN2 reaction. Then we also talked about this diazomethane, which would always give me the methyl ester, but it's still a way of making an ester. Okay, and then we also talked about how we could convert this to the acid chloride and then react this with alcohol, and we could convert this to the ester. So we've talked about a lot of ways. This is all review. But all of these are ways of preparing esters. So, you don't really even need this in your notes because it's already there. Okay? But that's going to bring us to reactions of esters. So what reactions will esters undergo? Okay, well, I'll give you just a kind of a hint of where we're going to move in the next lecture, and that is the first thing we're going to talk about is hydrolysis. And that's going to be the reaction of an ester with water. Okay, and so if I have an ester and I react it with water, and let's just use an arrow, what is my product going to be? What's in the box gets substituted for what the nucleophile is, and so I know that the result is going to be a carboxylic acid. And we can look at that mechanistically next time to make sure that you're up on it. But it's basically, again, nucleophile reacts with the electrophilic carbon, and the carbonyl moves the electrons up to the O, forming that tetrahedral intermediate, and then the electrons come back in to reform the pi bond, and then your leaving group leaves. Because what's in the box gets replaced with the nucleophile. Okay? That's what all these reactions are going to be. All right? So until next time.